start recording and go. And you have to finish this by
So for today, we're going to talk about tangent spaces of manifolds. Okay. So intuitively, we sort of know what a tangent space is. Let's look at it intuitively and see if we can get a few properties that we want. And let's see how our definition satisfies those properties. Okay. So let's say you have a sphere. Like this is sort of what we imagine a tangent space to look like. And notice that we want it to be a vector space. So if this point is on the tangent space, if I scale it by some scalar, then it should also be on the tangent space. And I should also be able to add two things that are in a tangent space. So let's say I have another vector here. I should be able to add them and get another vector that's in a tangent space. So we want it to be a vector space. Okay. In particular, we want it to be the same dimension as the manifold. And later we will prove that our definition does satisfy this property. And another intuitive way of thinking about a tangent space is that you want to be able to, it's sort of all possible, let's say this is a point on the manifold. The tangent space should contain all possible directions that you could travel in when you're at this point P. And one way that you can capture this information is to look at all possible derivatives at this point. Okay, so let's say you have some sort of manifold and a point on it, and you could look at the possible paths through this point. And if you only care about the direction that you can travel exactly at this point, you can just look at the velocity vector. So let's say this path is gamma from R to M. Then we want to look at, and gamma of 0 is equal to P. Then you want to look at the derivative of gamma at 0. All right. So basically, we want our tangent space to be some sort of derivative. And we know that derivatives satisfy the product rule, which is this. If so, I have times p of x, we want this derivative to satisfy the product rule as well. So our first definition is going to be of the tangent space is going to be so this is the tangent space at P of M is space of linear maps B from C infinity M, and this denotes all smooth functions from M to R. Yes, so V takes in a smooth function and outputs a number, satisfying so yes, we want all functions that satisfy all linear maps that satisfy the product rule, which is V of Fg is equal to V of F times G at P plus F at P times V of G. And notice that this V depends on the point. Okay, so that's our first definition.
So I think you should stop, take a sip of tea, maybe ask people a question.
Is it immediately obvious that it's a vector space?
Is it obvious why we define this to be the tangent space from the motivation provided?
Repeat the question.
So why is this the definition?
Very loosely, we want to be able to connect what we did 2 lectures ago on a manifold.
Yeah, that's roughly right.
But like more specifically, like, why this? I guess that's the question.
Well, okay, answer the question.
Okay. We're going to give another definition and prove that they're equivalent. And the other definition will be more intuitive.
Sure, but that doesn't connect what you said there to what you said here. Just
Right.
say the obvious thing.
Like the connection between.
Summarize. You said a bunch of things. Summarize them.
Okay. We want to define tangent spaces so that they have 2 properties. Like from intuition, we want them to be a vector space.
So sorry.
And
let's just go back. And
okay.
when we say tangent space, what I want to say is I have some manifold. I'm at a point, and I want to see what are all of the directions that I can move in at that point. That's what I mean.
Right. Derivatives.
And then, yes, okay, sure. And so then, if we want to see, what do directions do? And then you say that directions are
the same as derivatives. There's like a 1-to-1 correspondence between them. So we want to look at derivatives and derivatives of the product rule.
Yes.
And
what derivatives do is they act on functions. A derivative at a point acts on functions, gives you a number. So let's instead of looking at like obvious way. Let's look at things that act on functions and have the product rule, and hopefully that's going to be what we want at a particular point P in the manifold. Following question. Yeah.
Just clarifying the vision. V here is the V in the in the future to say V will be our derivative. V is a derivative.
V will be the same as derivative.
And then F of G and G of P because right above P. Thank you.
F and G are just functions, right? So V is something that takes in a function, outputs a number.
Well, we're specifying the point, right? That's why the P is there.
Yes. So I would say the tangent space TPM at the point.
Okay.
So we're looking at the directions I can go in if I'm standing at point.
Okay. Thank you.
Oh, sorry. This probably shouldn't be M. It's just some open set containing P.
Yeah, sure. Yeah. The thing is, it's the same. It's always the same because if I have like any function on U, I can always extend it to a function on M, where it's it's the thing you want on U, and then outside it's like 0 or something like this. You can always do like some bump function thing.
No.
Can you know?
No, like if you have 1 over x on like 0 to infinity.
That's okay, sure. But sorry, isn't it? Look, no, we wrote C infinity over M, so then F is just smooth everywhere on that.
Huh?
I want F to be smooth everywhere on F.
F doesn't have to be defined on the entirety of M.
Well, then you have to change what you write for V.
Oh, that's true.
So,
the
but
book does
the
say
point is, I think this wouldn't matter. Because I can have something like 1 over x, but then once again, I can make it outside of, like, where around P, I can make it to be like 1 over x, and then outside I can, like, bump function it to make it 0. So it will look like 1 over x as to where I want it to, where I want it to be, and 0 outside. So there will be something in C infinity of M that looks like 1 over x locally.
Okay.
So
yeah.
we need not worry about these guys at the moment. Maybe there's some edge case, but it's like it should not.
I think second V is supposed to represent the direction derivative, right? Derivative is supposed to be direction. Is that what we're going to represent?
I guess given a function, I guess.
So
yes.
It's a yes or no question. Yes.
So what's the normal derivative themselves could be added? What's the intuition that we can add derivatives here? I mean the operations themselves.
The intuition behind it, or how you formally add it?
Basically. Like derivative with respect to y and derivative with respect to x, we're going to add these operations together and get a derivative-like function.
Oh no, the direction is kind of like comes from the input, because f is a function from m to r, and that. Sorry.
So
No. So it's not a directional derivative.
No.
Wait.
He's right. V will be a directional derivative in some direction. That's fine.
It's the sum of.
Yes. So but that's the point. The point is that if I take a derivative in x and add it to a derivative in y, that's the same as taking a derivative in the direction 1, 1. Remember, this was something that I made a point about on the very, very first day. that when we say derivative in the kind of general sense from Rm to Rn, I want to find the best linear approximation, the best linear map. And then we define directional derivatives as I take this linear map and apply it to E1, E2 up to all the basic. So then if I want to take a best linear approximation in some E1 plus here, this is a linear map. It would be just D applied to E1 plus D applied to E2. So if you have a directional derivative along x1, and then you have a directional derivative along x2, and then you add them together, that is the same as taking a directional derivative along 1, 1. Now note that 1, 1 is not normalized. So it's like if you're differentiating going like root 2 faster than you normally would. But that's in what sense that you can add these. That's why I want to add them. And that's why it's precisely like adding directions. Like this is like exactly the same as adding directions. Instead of v is like I take a derivative in a certain direction, but then I can add them together to get a new direction, and then this new v corresponds to taking a derivative in this new direction.
So in some sense, we're not representing the vector space, we're representing the direction of the vector space, and then later turn that like into a whole vector space. What's your there?
I mean, it already is a vector space. It's the set of linear maps on some linear space. It's a vector space.
Yeah, but I mean, right now it's not like the vector space we see in some sense.
What it will be isomorphic to the vector. Like it's isomorphic, so this is what we want already. We already have it. It's just that we can understand it in a way that it's easier for us to understand. But this is already what we want, and this is a good language to use for it, because this is quite literally the same as a direction. Like a direction is the same as taking a derivative in that direction, and then adding two directions, and then taking a derivative in that is the same as adding the derivatives in those two directions. You were gonna say?
I was just gonna say you said stuff nicer. I was just gonna say I don't know if it's helpful for people just like identifying what if I wrote like v to v with like for example the product rule, just like the d by dx is like an example of v. And just like in one dimension, it's like those things are saying the same thing if you understand d by dx to be your v.
And we will show this in a second. We will show that this set of things is precisely the set of derivatives. Okay, but does the idea make sense?
Yes, great.
And yeah, remember that. Enjoy your donut. Remember that. Yeah, like this fact about like taking a derivative this way and this way is the same as taking a derivative in this along this slightly longer vector. This is, I never proved this, but okay, that's how it is.
What about from that to see by taking the derivative, like if you have the derivative with respect to v and like lambda v are the same.
Taking a directional derivative along v and lambda v, the derivative is not the same, it's scaled by lambda, by product rule. Not product rule, by chain rule. If I scale along, if I take a derivative in the direction lambda v, right, then the derivative I should get out should be lambda times the derivative along v, right? Because when you take these derivatives, what do you mean? You mean df dt, sorry, d dt of f of p plus tv, right? So, and you take the derivative at t equals 0. So then if I put a lambda in front of the t, then I get the same derivative, but just scaled by lambda. So yeah, this is the thing, that you're not just taking a derivative in the direction, you're taking the derivative in a direction plus like a certain speed, which is the size of your vector. So yeah, the derivative in the direction 1, 1 is not the same as the derivative in the direction 1 over root 2, 1 over root 2. There's like a scaling factor difference. But Otherwise, it's the thing. Okay. Does that help clarify?
Just like,
Okay. Ife, does that help clarify?
Yes.
Okay.
Okay.
Very cool.
Then I'll move on to the second definition and prove that they are equivalent. Um, so this one depends on a choice of charts. That U phi BA chart. Around the point P, so P is in U. And the tangent space is defined to be a set of linear maps again, V is from C infinity M to R. That's in the form V applied to F is equal to the sum over I from the second definition, it's more obvious that this is about directions. This is
Okay, so one thing is maybe just not to be pedantic, you want to take the derivative at the point that, you know, phi inverse of P or something like that. And so one thing that in the future we will very often write, we will write V to just be equal to AI partial partial xi. Can you just write that like somewhere in the corner? I don't know. V equals AI, sum AI partial xi. Yes. So people operate it. So it's just some differential operator.
yes.
Actually, where the indices go matters. If they go like lower or upper, because of various conventions. Like at a certain point, it starts mattering where the indices go, especially in physics. Because in physics, where the indices go actually like starts meaning something that's not.
I was gonna ask you, because in my textbook, for the coordinates, they put the indices as superscript. Like, is there a reason?
Yes. There's a reason that superscript and lower script at some point are not quite the same, and there's some difference.
Should we continue to use superscript?
You should use whatever the book uses and stick with the book's convention.
Okay.
Because our book's convention, I think, is pretty is good. Okay.
Okay. So we first want to check that definition 2 is actually about directional derivatives. Okay. Okay. Let's V be a linear map as in definition 2. And that gamma tilde be a curve from R to phi of U, such that it's just a like straight line through phi of P with this is A, where A is equal to okay. Okay, and then we define, oh, sorry, this is gamma tilde. And now we define gamma of T to be equal to, sorry, you can just write equal to phi inverse composed with gamma tilde. So basically, what we want to show is that it's the directional.
Just give them.
Bro, I disconnect my AirPods and just play it out loud. Yeah.
Okay. Now go.
Quick check. Should that just be P instead of phi inverse? That's the evaluation.
Yeah.
Something's inconsistent.
Oh, true, because I already wrote phi inverse here.
And then you're evaluating both like phi at P, and then you wrote phi inverse at P.
Phi is from U to R, and P is the point in U.
So over there, how do we want phi at P instead of phi inverse at P? So that
No, we want phi inverse, and we want to do it at phi of P. Like, I only know how to take derivatives of maps in Rn.
yeah, so I'm saying like we should evaluate at phi.
So phi goes from the manifold to the coordinates, right?
Right, so it is phi.
So that is phi of P. That's fine.
It's phi.
Phi, at least in our convention, phi goes from the manifold to the coordinates. So what we do is we start in the coordinates, we go back to the manifold with phi inverse, we evaluate the function f, and then we get this, and now this is a nice map from Rn to R. I know how to take that derivative. Yeah, it's just our convention of how we do charts. Some things do from U to the manifold. We're doing from the manifold to Rn. Yeah.
For definition 1, is it significant that we only wrote R instead of R?
It's not, because if I look at a function to Rn, that's really just a function, a bunch of functions to R.
Oh.
And so it's the same.
Okay. So like checking that definition 2 is basically directional derivatives. We want to prove that v of f is in the form f compose gamma of t at t is equal to 0. Okay. So we just substitute this in here. And notice that this is a function from Rn to R, and this is a function from R to Rn. Sorry.
That's right.
Yeah. Okay, so we can apply the usual chain rule. Right. Zero times wait. Oh yes. Times gamma tilde of 0, because gamma is linear, so the derivative is itself. Yeah. Oh, sorry. I forgot that this is a. Sorry. That was a mistake. Because this is from R to Rn. So we use the a different chain rule. Should be gamma I. This is partial x. Okay. And this is just a number, and that's the AI here. And this is equal to just 5p. Okay. Are there any questions?
You have to have a question by default.
I'm reading it. Yeah, I'm trying to get it. Wait, I do have one question. Where's the AI?
It's just any real
So
number.
it's just you look at the set of all things that look like this for some AI. You have to.
Superscript, subscript check on the X.
Yeah.
Let's see if we get it more.
Yeah. So. Yeah.
This is just to show the AI whatever it's just gamma, and it does take this form.
Yeah.
Okay.
And then we're going to show that definition 1 and 2 are equivalent.
Yeah, that definition doesn't make sense, and we're gonna.
Can I erase this?
Can I take a picture? Thank you.
Take the derivative along.
My point of view will push this one aside.
Oh. Okay. We're going to prove the difficult direction first, which is 1 implies 2. implies to.
Just to clarify, we're saying that if you can do product rule on this set of linear maps, then you can by default do this.
Yeah.
Sorry, what's the
Like proof of one implies to is saying if your set of linear maps satisfies product rule, then it also can take the form, whatever that is.
so yeah, so the point is that if I have that that the claim is one implies two. Well, maybe you should say what's the non-trivial claim in one implies two.
Well,
It's
What do
quite
you-
strong. That's what like, intuitively.
sorry, what do you mean?
What's the claim of one implies two?
Oh, it's just any linear map satisfying these properties, the product rule, can be written in this form.
Yeah. Okay.
In coordinates. That's it.
Okay.
And I mean, it's kind of expected. Like, derivatives were something that acts on functions are linear and have product rule, and we said let's look at something that is acts on functions is linear and has product rule, and then we realized that's just the same as the derivatives. Okay.
Maybe notation got it. Thank you.
Who would have thought? Well, actually, no. Maybe we could have imagined that there's something more to derivatives than product rule, but actually, I guess that's all there is to it. Okay.
Okay. So we first need to prove a lemma. Called Hadamard's lemma. Which states, if U is an open ball, with radius r around 0 in Rm, obviously you have r is greater than 0, and h is a smooth function on u. Yes, u. And this means from u to r. Then there exists hi. Also smooth functions on u, such that h of u is equal to h of 0 plus the sum of I to 1 to m ui, where this is a component of u, times hi at 0. Sorry, not 0, u. And hi has the properties that for all, so this is true for all u and u. And then we also have that hi of 0 is equal to partial h partial ui at 0.
Give me a moment. Let me just U is some open ball. H is a smooth function. But then there exist hi's which are smooth functions. Such that h of u. So h of u is a set.
No, lowercase u is
for all of
a
u.
point in u.
Is equal to ui
It's like a very primitive form of our
Yeah.
derivative demonstration.
So is H2 RM or U or something, and is HI just R?
Hi is to r.
yes.
H is to R.
Yes.
H is a
That's what this notation means.
Yeah, C infinity on U.
This is defined
So-
here.
Okay.
C infinity of C infinity of something implies from that something to R.
So H is not R.
H is from H is
So that's what we're saying though. Like if you have components, then you should obviously have higher dimension. You can't both be R.
no, H takes in R vectors in our M, outputs a number. That's it's consistent. U, capital U, is a vector in R, is some set of vectors in R. I plug them into H, I get a single number.
What exactly are our HIs? Like there is just some HI. Like what's this?
Is there some picture for this?
The proof will give you an explicit formula for it.
Okay.
And the second one?
Here? No, they're numbers.
They're just numbers.
U is
Okay.
U is equal to
Yeah, they are components of a vector. And I guess here you want upper.
No, I bet something. It's just not a legit copy. Like a really rough skeleton of what we said in like the first lecture. Like what is it? You center it on this point and then give your linear approximations in M dimensions.
Yes, that is
Roughly.
similar, but it's not quite the same. Sorry. The statement is that the HIs of 0 are the derivatives in UI. Yeah, do I not need some like correction term then?
correction term?
What's
What
the, is
correction
this the
term?
actual statement of pattern works on?
So what do you mean by correction term?
Sorry, let me just. Oh, okay, yeah, sure, sure.
This is U is a subset of RM.
Yeah.
So
yeah,
you can
this
write
is
it in
fine,
components.
this is fine, I agree. Okay.
Proof.
So this is kind of not close.
Sorry.
It's close. This is close. This is close to just like taking a derivative and saying that H of U is like H0 plus some derivatives, but it's not quite. Anyways, keep going. Sorry.
Okay. So for some U, for some let's say fix U in this open set U, and we consider the function that takes t to t times u1 up to t times un. Multiplied by t in each component. And then we have h of u minus h of 0 is equal to the integral from 0 to 1 d dt of, I guess, sorry, define h to be this function. Sorry, no. Sorry. H is given. H of tu dt. And this is just by the fundamental theorem of calculus.
Can you see this?
Sorry. Yeah. Yes.
And the next step is basically just differentiate this. So this is the integral from 0 to 1. Sum from is1 to n. Sorry. partial. Sorry. Yeah, sorry. It was correct. Partial h, partial ui. Okay. This step is basically just the chain rule. Yeah. Okay.
Thank you so much.
Yeah. And then where?
Now
Oh,
you're just
sorry.
integrating over t, so you can just factor out the ui's.
I'm going to switch the sum and the integral sign because this is a finite sum. So, oh yes, the integral of them. UI. Yes. And then we can just define this to be hi. And what's left to prove is that hi of 0 is equal to partial h partial ui at 0.
If you're writing something there, like make a dotted line that separates, the stuff below and above for your.
Let's just check if this is true. Partial h partial ui of u is equal to we just plug in this formula. So that's equal to partial ui of h of 0. And this applied to this constant term is 0, and then when you apply it here, you apply the product rule when this. Sorry, I shouldn't have used I. So when I is equal to j, you apply the product rule, and then otherwise you treat this as a constant. And this gives you hi of u plus sum over j. And then if you apply, sorry, a value of both sides is 0, that gives you, this is equal to, evaluate at u is equal to 0, and that gives you partial h partial ui at 0 is equal to hi of 0. And then we're going to prove the theorem. Can I erase the proof?
Give people a moment.
Okay.
delete this. Good.
And we're going to prove 1 implies 2 in 3 steps. Step 1. We want to show that if you have 2 functions that are equal on a neighborhood around P, then V applied to these 2 functions are the same. Okay. And then step 2 is we are going to define a linear map V tilde on C infinity U to R with the same kind of properties. We want to define it such that V tilde applied to F tilde is equal to V of F, where V is a linear map that satisfies the product rule. That's on C infinity M, and F tilde is equal to F compose phi inverse restricted to U. Actually, it doesn't have to be U. Some neighborhood in U, well, some open neighborhood around the point P. Okay, and step 3 is apply the lemma. Let's do step 1. So let's say we have F1 is equal to F2 on some open set containing P. Then we can define another function to be the difference between F1 and F2. And it's sufficient to prove that V applied to F is equal to 0 because V is linear. And then we want to choose a C infinity bump function. Let's say let's call it Chi. And by bump function I mean that chi applied to P is equal to 1, and chi is equal to 0, for all x that's not in and do people know how to find a bump function, or should I give an do people know how to find a bump function, or should I give an explicit formula for it? Have you taken 257? Okay. So let's first look at the function h from R to R, and h takes x to e to the negative 1 minus x squared. This function should look something like this. Wait, is this what I need? Yes.
Are you
And
writing something on this board?
this,
Because if you are, then the video cannot see this.
oh, that's true. Oh, sorry. Wait.
At 1, you just define it to be equal to 0. Because you have e to the minus, like, essentially infinity. So you can continuously just define it by hand there, and then it will still be continuous.
Right, and this is actually not 1 here, but we can just multiply this by some constant to make it 1. I'm not going to bother figuring out what the constant is. And then we can define another function. We can define chi to be h of the norm of x minus p. Sorry. Actually, no, I don't want this. I want
Yes. There we go.
now I can define chi.
Yeah, so what is this?
Oh, actually, this cannot be 1. This has to be. What's the problem?
It should be whatever the size of the epsilon bond is.
Yeah, I should say that let this be contained in U.
Yeah.
And this should
X
be
is greater than
this should be
epsilon.
well, actually, I can just do this.
Okay, sure. So what is this chi function?
Well, chi is equal to 1 on, well, okay, the goal is to multiply f by chi.
Okay,
And when
why?
it's equal
Like,
to what
what
is
chi?
it looks like this.
Yeah, okay, so you have your manifold, right? And you have some point P, which you want to study, and you want to like show that oh, this is the part that we, like I said, is not important by just changing that definition, but I guess you're proving it now anyway. But the point is, what are we trying to do? We want to show that for any function that's you have a point M, so you have a manifold M, you have a point P in the manifold. And suppose you have a function that is only defined like locally in some open set around U, okay? Around the point. And it's smooth, and this function is smooth in this like little open ball. What you want to say is that for any function like this, there should be some function that agrees with this one, and it will be defined on kind of the whole of the whole manifold. So for any like smooth function locally, it can be extended to a smooth function on the whole manifold. How are we going to do this? We're just going to look at this. We're going to use this chi thing, which is like 1 around very close to P, and then smoothly decays to be 0, like a little bit further away. And so then we're going to take our function and kind of multiply this by this chi and extend it to be something that's like this function in a little vicinity, and then smoothly decays to 0 everywhere else. And then we can just extend it to be 0 everywhere else in the manifold. Just sending to 0 is always going to be a smooth function. And this is what I was saying, like, oh, don't worry about making it like U to R because it doesn't matter anyway because of this. And I didn't know you're going to talk about it, but that's okay. Now we're showing it explicitly.
Right. One thing to note is that this works if you don't care about how. Do you want like chi multiplied by some function to be equal to that function on some kind of set? But this only works if you don't care about how small that set is, or if that set is closed.
Yes.
So, like, if you have an open set in general, you can't have, you can't extend any function on that open set to, like, everywhere in a manifold.
If the function, you can only extend the function defined on like a sufficiently small set around the point. Perhaps a counterexample will be an exercise.
So we just apply V to chi multiplied by F. And by the product rule, it's just V of chi times F at P plus chi at P times V of F. And this is 1.
And you also want to compute V of chi.
Right. I need to compute. So wait.
V of chi at P, but V of chi at P should be V is some direction derivative of this bump function chi at the point P where the bump function is set. What should that be? 0, yeah, because it's gonna be flat. Yeah.
Wait, why is F of chi 0?
Why is F of chi 0?
F times chi.
F times chi?
Sorry, V of F times chi.
V of F times chi is not 0. It's just V of F.
The whole point is to prove that V of F is 0.
No, you want to show that V of X, you want to show that V of F is equal to V of chi times F at P. That's what you want to show.
No, because f1 and f2 are equal on an open
On this
set.
open set U. That's
Yeah,
right.
and then f is the difference. So
Oh
I'm-
yeah. Okay.
yeah,
Sure.
I'm trying to
then it's 0. Yes, you're right. Then it's 0.
Wait.
Why? Because v of f is going to be.
Oh, okay.
V
Yes,
of f
I
is
see.
0
I see.
just because they're the same function on the small set U.
Yes. Okay. I see. Yes, I see now. Yeah, this is always 0
Yeah.
because on U you have
They
f
agree.
is equal to 0, and then outside of U, chi is equal to 0. So this is equal to 0.
Yeah.
And now it's sufficient to show that v of chi is equal to 1.
Yes. We can. That's just computing a. What is v? Is it according to definition 1 or definition 2?
Definition 1.
Ah, okay. Yeah, go ahead.
Confused.
V of chi is equal to 0. Well, v of chi is just v of some constant function because this is all the linear maps that take functions on U and do whatever. And so then you can probably show by, so chi on this open set U is equal to chi squared, right? So then you get that chi is equal to, by product rule, v of chi squared is equal to v of chi is equal to v of chi plus v of chi, and so it has to be 0.
Oh, okay.
So that's how you would do it. But once again, we kind of messed this up because we wrote the definition for C infinity m instead of C infinity u, which is actually yeah, whatever.
And then this is equal to 1, so that's equal to 2 times v of chi.
Yes. No, but yes, and the chi squared is equal to chi on U. So 2 v of chi is equal to v of chi.
No, chi squared is not equal to it.
Isn't it? Oh, right, it's not equal.
No.
Sorry, you're right. Chi squared is not just 1. Oh. Then what is it? This should be somehow enough to conclude everything.
Why are we not done?
Because we defined V to be this sorry, it's not clear how to show that this V of chi is 0.
Why v of chi 0?
Yes.
Not using f of p 0?
Well, we don't.
Oh, true. I'm so stupid.
Yeah. Right.
We're done. We're done. This is okay. Sorry. This is equal to 0, which means this is just equal to v of f. Yes. Okay. We're done. This is step 1. Yes. Okay. Let me erase this and prove step 2 here.
So maybe every detail is hard to catch. In in general, this is a common idea where if you want to, you have some function defined on some sufficiently small set, you want to extend it to a function on the whole thing, you just like multiply it by some like bump function, so that in some region it's like 1, and then outside it's 0, and then you just extend it to be like this thing that's the right thing on the small interval, and then 0 everywhere else, using these bump functions.
Okay. Basically, step 2 is we define this, and the only thing that we need to do is to check that this is actually well defined.
Okay.
So, okay. So basically, suppose G is equal to compose phi inverse on U. Then G is equal to F tilde on U. And then by step 1, V of G, V tilde of G is equal to V tilde of F tilde. So this is well defined. Steps.
You erased too fast, and no one noticed what you wrote.
Okay. Let me just restate it. We just need to check that this V tilde is well defined.
So what we want to do is we have some set of things in definition 2. We have some set of things in definition 1. We want to map a V in definition 1 to what? Sorry, what is this map?
V tilde? Or,
oh yes, sorry. Yes, we
yes.
have a V of F is something that takes in functions on the smooth functions on the manifold outputs.
Oh, sorry, this is incorrect.
Outputs things, and then I want to turn it into something that takes in functions on like a coordinate patch, and then outputs a number.
Yeah.
So that I can prep it for definition 2. Right?
So step 2 is basically make sure that we can apply the lemma, because like V is defined on C infinity M.
Yeah.
And we want to define something else that's on from like smooth functions on an open set in Rn to R.
That's right.
Yes, so we check that this is well defined. If
yeah, on phi of U, that's right. Phi inverse is defined on phi of U, not mu. You have F twiddle, it's phi of U. That's right. U is
oh
the
yes.
manifold.
Yes. If G is equal to F compose phi inverse on phi of U, then basically by step 1, because it's equal to F tilde on this restriction. So by step 1, V of G is equal to V tilde. Oh, sorry. This is V tilde. Yes. So this shows that this V tilde is well defined.
F tilde is
Yes, they're defined.
field of G is equal to B field of G.
So it's not then, it's just like, that's the definition. And the point is, by step one, this is a definition that makes sense. I think that's all this is trying to say. Step one was to show that if I have a function, I can extend it. If I have a function on an open set, I can extend it to a function on the whole manifold, which will agree such that V of F will agree with for both of them.
Yeah, but you're not extending G and F tilde, which are the same thing, defined on field U. The functions on field U, so you can't extend them in the maybe you can extend them to the whole Rn.
You can extend, no, you can extend, yeah, sorry, yes. You can take G and extend it in, G is a function given in coordinates. So this is a function, G is a function on some open set U. And the claim is that
G is a function on field.
Okay, sorry. G is some function in coordinates, and then I can write G to be some function that is just defined on U, and then I can extend this some function defined on U to a function on the whole manifold, which is close enough to F in coordinates around the point P and 0 everywhere else. And this is necessary. I forget why. It's some pedantic thing about having something defined on the whole manifold versus in some chart U.
Oh, sorry. This is not what I meant to say.
Okay, maybe it's not.
This is not.
What's supposed to be done?
It's just maybe I should, just some open set containing P,
Okay.
where P is in W. It's contained in 5U.
U
Yes, phi of P belongs to W. If W is a subset of phi of U, then phi of P has to.
Oh, sorry.
Sorry, so following question. How did you define V tilde?
Well, V tilde of some function. It's a smooth function on 5U.
Right. The claim is I want to define something that takes in functions in coordinates in a particular coordinate chart, outputs a number, and I want to yes, and I want to define that somehow in terms of yes, I want to use V to be something that takes in maps defined in a coordinate chart.
Yes, I mean, I think the point of this is you have a function on your chart.
Yes.
That's not necessarily extendable to the whole manifold.
Yes.
So you can't really define V tilde just applying V to that function on the chart. So the point of saying that V tilde is well defined is you want to take that function on the chart, you want to multiply it by one function to get the function on the whole
That's right.
then apply V. And then you have to show that this is independent of using the function.
Well, that's too much. We chose a particular bump function, and we just want to show that it's that you can just do this for our particular trace of bump function, and that that trace of bump function would agree with. I guess we did show. Yes, we did show that it's independent of the trace of bump because of you have f1 is equal to f2. Okay.
So this is like if it's equal on some other open set. Let's say V. Then G is equal to f tilde restricted to v intersect w. And this is still open, and so you have, by step 1, you have this.
Okay. Sure.
Um, oh, okay. We want to show that this is equal to 1, and we've already shown that this implies something else, which was it erased? Yes. So this shows that definition 2 is independent of coordinates.
Yes.
Which means right, so, and that means where is it? Okay. We can assume that phi of g is equal to 0.
Okay.
And then say u tilde is then 0. There's an open set containing 0. And then we have v tilde as in step 2. And then given a function m, infinite, we define f tilde to be, it's given a chart by inverse. Okay. And we are going to write f tilde using Hadamard's lemma. Let's call them f. And then each fi is a smooth function on M. And we also have fi at 0 is equal to partial f partial xi at 0. Yes. Okay. And we apply then v of f is equal to v tilde of f tilde And because it's linear, this is equal to 0. Well, actually, this is a constant, so v applied to this is equal to 0. And v tilde also satisfies the product rule. Which means sorry. Zero, and this should be 0, and that's and then we just let this be AI in this definition over here. So that's the proof of 1 implies 2. Should I erase? Or
So I think, what were we going to do next?
2 implies 1.
2 implies 1. If you're reading there, let's see.
Um, 2 implies 1 is a fairly straightforward computation. So we just apply the v in definition to fg.
I mean, the 2 to 1 is. Wait a second, keep going. Two implies 1 is straightforward. All she's doing is you just you take something that's defined on some open chart U, okay? You have these v's that are defined on these open charts U, but okay, if you have any function on the whole manifold, you can always write it in the open chart, and so then you immediately have something that takes a function on the whole thing, restricts it to an open chart, takes the derivative, and that's precisely something that does definition 1. And so okay, then you can just like write out the chain rule for derivatives. Okay, that's maybe clear. Okay, so we've learned what a tangent space at a point is, and the first definition is kind of how to write this thing generally, and the second definition is how to write v in some particular choice of coordinates. Okay? So one thing that would be or that maybe we'll do next time, is look at how to switch coordinates and some things like this, and we'll look at finally Lie brackets. But that will be later. I think now that we've essentially shown that these two definitions are equivalent, is a good time to stop. Or
Okay.
okay. Yes. Sounds good. Thank you, Ife.